Morning.
Hey, how's it going? Cool, let's get started. Sweet. So today is going to be lecture 25. I believe this is the last in-person lecture for section 6. Correct me if I'm wrong, but I'm pretty sure that's true. So this is going to be our last required meeting in person, basically. So one thing I'll say before we begin our lecture is it's been an awesome ride. I've been super happy with how this class has gone, how excited people have been about learning new things, and overall, everyone's been so engaged. Everyone has really embraced a lot of the philosophies that we talked about on day one, and I'm really, really going to miss working with you guys in a couple weeks. I'm not just saying that, like, I really, really will. I think it's been an awesome time, and I just wanted to thank you for being awesome students so far. That being said, let's start talking about today's lecture, which is going to be on skip lists. So we have 3 lectures remaining. Today is going to focus on data structures. I think I haven't planned these out yet, but Monday I'm probably also going to be talking about complexity and data structures. And then Wednesday is going to be more of an open-ended topic, and it's going to be talking about things that you should know before you jump into your job on day one. Basically things that your employer is going to expect you to know if you take a software engineering job, but no one really teaches you in detail about those things. And some of the things that we're going to be covering are, for example, design patterns, how to engineer efficiently, why you shouldn't be taking shortcuts, and things like that. So we're going to be covering those. So those are going to be the next 3 lectures and our final 3 lectures. Cool. So a couple announcements. Homework 4, I believe, is due today. It was either due yesterday or due today. I don't really know, and I don't really care. So make sure you turn it in as soon as you finish grading. So wait, one sec. Today, okay, cool. So make sure you turn it in as soon as you finish grading. Please, please do that. That would be super helpful for me. Just because we have a lot of grading to do. We still have the projects to grade, the homework 4 and homework 5, and the final. So like, the sooner you get it graded, the sooner I can start grading it and get more feedback to you earlier for the final and stuff like that. So it's going to help both of us if you turn it in as soon as you finish it. So please don't just wait until tomorrow to turn it in or something. Just turn it in as soon as you're done. It should be pretty straightforward, so I hope that's not too much of an ask. Homework 5 has already been posted, so you can get started on it pretty much as soon as you want. And one thing I wanted to say is I would recommend getting started on it as soon as possible, because the final exam is probably going to be posted today or tomorrow. If you cannot finish today, is it going to lose credit if submitted tomorrow? No, it's not going to be going to lose credit, but if you could at least do like the written problems and submit those, that would be really helpful. The written problems shouldn't take much time at all. So something like that would be good. Cool. So the final exam is going to be a take home. It's going to be harder than the midterm. So if the midterm was pretty difficult for you, make sure you spend a decent amount of time on the final, because it's going to be pretty difficult. It's going to take a long amount of time. And I want you to be prepared to spend some time on it. This is a super important announcement. All assignments are due exactly at May 12th at 2 p.m., whether it's late work, on-time work, the final exam, homework 3, homework 4, homework 5, project 2, everything is due at May 12th at 2 p.m. It doesn't matter if we're taking the 50% penalty. If you don't turn it in by May 12th at 2 p.m., we're marking it as a 0. If you turn it in at 2:01 p.m. on May 12th, you are getting a 0 on it. So 2 p.m. is a hard deadline. So don't try to submit something at 1:55 p.m. and then say Canvas is down. So like don't try to like make excuses for why you couldn't turn it in. Turn it in 2 hours early. Email it to us if it doesn't work or something like that. But if the timestamp is after 2 p.m. on May 12th, you are automatically getting a 0 for everything that is not turned in. So that is a hard deadline. We are not going to have any exceptions for that. Cool. Any questions on any announcements? Okay, sweet. And May 12th at 2 p.m. is also the deadline for the final. So make sure that there's not going to be any late submissions for the final or anything. If you just don't turn in the final, you're going to get a 0 on the final, and that's going to tank your grade. So make sure you don't do that. Actually turn in the final. Whatever you have is good, but turn in by May 12th at 2 p.m. Cool. So couple objectives for today's lesson. So you will be, by the end of today's lecture, you should be able to understand how a skip list is different than a linked list or a BST. You should be able to evaluate the probabilistic average complexity of all skip list operations. And then individually, you should be able to implement a skip list. I'm going to modify that a little bit. You should be able to know how to. So this is going to be more of a theoretical lecture. We're not going to have a replit, unfortunately. I just honestly didn't have the time to make it last night. So we're just going to, you're just going to be able to figure out how to implement a skip list. You're not necessarily going to implement it in class or anything. So let's start with the partner exercise. We're going to talk about the complexity of a linked list, and they're going to have different characteristics. So what is the complexity of finding an element in an unsorted singly linked list? For those of you who don't know what a singly linked list is, a singly linked list means that a node has a pointer to its next, but not a pointer to its previous. So 3 points to 5, but 5 doesn't point to 3. So in an unsorted singly linked list, what is the complexity of finding an element? What is the complexity of inserting a new element into an unsorted singly linked list? What's the complexity of finding an element in a sorted singly linked list? And what's the complexity of inserting a new element into a sorted singly linked list? So take a minute and talk to partners and figure out what the answers are for A, B, C, and D. All right, let's jump into it. So Kevin, would you mind responding? Would you mind unmuting potentially or typing out your answers? What do you think the answers are for A, B, C, and D?
Hi. So for A, it's the O(n) and being the number of nodes in the list. And then B, inserting would be O1. C is and D is O of N.
And C is D, is C and D are both O of N. Okay. Why is B O of 1 and D O of N?
Since it's an unsorted linked list, you can just put it in the front without caring, but it's sorted, so you're gonna have to keep going through the linked list until you find the correct position.
Yep, sounds perfect. Yeah. So if we have something like 3, 5, 7, let's say this is an unsorted linked list, and you're just inserting a new element. Linked lists have a property where you can just basically, it keeps track of the last element at some point. So you can just say O of 1 here, because you can just say insert and it's going to keep track of the memory address at 7, and it's going to add the new element 9. However, let's say that we're actually inserting 6 into our linked list. So now this is a sorted linked list that we have 3, 5, 7 for. So as Kevin observed, we actually have to find the one where we have to find the right place where 6 is going to go. So we have to go through the linked list one at a time. We start at 3, then we go to 5, then we say 5's next element is going to be 6. And then 6's next element is 7. So then we erase this. But this could be an O of N operation because we have to go through the entire linked list starting at the head. So sure, isn't the last one going to be O of N minus 1? Yeah, but we ignore constants. So like N minus 1 is O of N. So don't forget that there are no constants in big O notation. So someone asked me privately, can't we do a binary search on a linked list? Why can't we do a binary search on a linked list? Kevin, do you want to respond to that?
I believe since it's a linked list, we can't just randomly jump around to parts of the list. Like we can only go in one direction.
Right. So a node in a linked list is going to have two attributes. It's going to have an int value, and it's going to have a node pointer. So for those of you in C++, I'll put the star, and it's going to be pointing to next. So how can we do a binary search on this? There's no way. You can't go backwards. You can't jump multiple elements to the front. The only thing you can do is go to the next element. And that's like the only thing that is possible. So you have to start at the front and go all the way to the back. The only other thing that you can do is insert. Actually, we say O of 1, like Kevin said, because we have some pointer to the last element in some sense. So I actually got this wrong. So this is going to be O of 1, O of N, like we said, and this is O of N. This is going to be theta of 1, and then this is going to be theta of N. So ignore this slide. This is not true. So Kevin is actually right. Thank you for that. I actually got that wrong. But what Kevin said was right. O of N, theta of 1, O of N, and theta of N. One thing that I wanted to mention here is we want to use the tightest bounds that we can. And actually, in fact, this is not theta of N either. This is O of N. So we want to use theta where we can use theta for full credit on the final. So if something has a theta value and you say O of 1 instead of theta of 1, then I'm probably going to take off a point or two. So make sure that you're being as tight as possible for your bounds wherever you can be. Cool. So let's do a search for the linked list node. So what a linked list search is going to look like is basically, let's say that we have the following linked list. So we have 376, and we're searching for a 6 here. So all we're going to do is basically say, this is a sorted linked list search. So for a sorted linked list, let's say that we have a 3, a 6, and a 7. And then we're searching for a 7, sorry. If something is O of 1, wouldn't that always be theta of 1? Yeah, so you can basically say theta of 1 all the time instead of O of 1. Great observation. Yep. Cool. So if we have a 3, 6, and a 7 and we're searching for a 7, what we're going to do is say cur is equal to 3. It's equal to our head. While it's not equal to none, we're going to compare the value 7 versus the 3. If 7 is higher, we just go to the next node. So we go from 3 to 6, and we say, is 7 higher? Then yes, it is. So we go to the next node, and this is a 7. And we say here, if the value is equal to the goal, we just return the head, or sorry, not the head. Sorry, there are a few mistakes on these slides. I'm not sure why. Maybe because I did them really late at night. But we're going to return the cur, so the current node basically that has the 7. But if we're searching for, let's say we're searching for 6.5 here. So this is the 7. Let's say we're searching for 6.5. Then we're going to get to 7, and then we're going to be like, 7 is actually higher than 6.5. So we're going to end up returning none here, basically. So if it's greater than the goal, then we return none. And then lastly, we do a search on, let's say we're searching for 8. Once we exit out of this while loop here, we're just going to return none and say our value is greater than any value in the linked list. Does this make sense? The sorted linked list search? All we're doing is going one element at a time. We're doing a linear search down the entire linked list. Yep. Cool. So that is how we can do this search. The only thing that would change here, how would we actually change this if this were an unsorted linked list? So let's say we have a 3 going to a 7 going to a 6. How would we change this logic and make it pretty similar, but for an unsorted linked list? Anybody raise your hands?
Sorry, can you repeat the question?
Yeah, so how would we change the logic, like the current code that we have, if it were an unsorted linked list, not just a sorted one? David? Remove the second if condition. The second if condition, so if curval equals goal. No worries. Okay, the first one. Okay. So all we have to do is take this out. So for an unsorted linked list, let's just comment these out. And then all we have to do is say if cur val equals the goal, then you return the cur. Otherwise, you go to the next one. Exactly. So all we're doing is removing this condition, and otherwise the logic is exactly the same for an unsorted linked list. Does that make sense to everyone? Yep. Any questions? Cool. So sorted is omega 1. Well, I mean, yes. So sorted would be omega 1, but so would unsorted. So it could be the first element in both cases. But yeah, the average is probably going to be going to be O of n, and then the worst case scenario is also going to be O of n. So let me write those down for those of us who weren't listening. So we have best, average, worst, and we have unsorted, and we have a sorted. Okay, so the best case is going to be omega of 1 because it's the first element that you're looking for. Your average is probably going to be in the realm of O of n. And then your worst case scenario is going to be O of n as well. Does that make sense? Everyone with me so far? This should all be recap. We should be able to see all of these linked list operations follow pretty easily. Okay. So let's ask ourselves, can't we do better than this? The algorithm for search in a sorted and the unsorted is almost the same. There was just 2 lines that make a difference, and they don't change the complexity of the operations much at all. They're both going to be O of n average and O of n worst. But that's really bad, right? So we know that the sorted, with a sorted array versus an unsorted array, the complexity is dramatically different. So let's talk about that for a sec. So we have best, average, and worst for a sorted list and an unsorted list. So what does that look like? Anybody have thoughts? What is the best case complexity of these two? Any thoughts? So we're not talking about a linked list here. We're just talking about an array. David? Constant time. Yeah. So we have omega 1 for both of these. What about average? Anybody have ideas of what the average runtime is for a sorted list? How do we do the average runtime to find something in a sorted list? Do you remember the first algorithm that you probably did in your first algorithms class? So if we have a sorted list, yeah, we can do a binary search. And what is the average runtime of binary search? Log n, exactly. So this is going to be log n, and then the worst case scenario is also going to be log n because we're doing a binary search. And then after that, we can say that the unsorted list is going to be O of n, and the worst case scenario is also going to be O of n. Does that sound good? Cool. So that is what we're looking at for a sorted list and an unsorted list. In an array, we actually see dramatically different log n and n values, basically. So it's going to be much easier for us to search in a sorted list versus an unsorted list. But the problem here is, let's say we have a sorted linked list, then this is going to be the same. It's going to be O of n for both a sorted linked list and an unsorted linked list, which is not something that we like. So how can we do better? Can we do something to improve this algorithm and actually cut down on the amount of lookup time if it's sorted? So that's going to be what we're going to be answering in class today. So let's jump right into a whiteboarding exercise. So we have a sorted list here. So we have 14, 23, 34, 42, et cetera, et cetera. Okay. Does anybody recognize these numbers out of chance? Anybody who go to New York? Not really.
Subway line?
14th, yeah, 14th Street, 23rd Street, 34th. Yeah, this is my subway that I took to get to NJIT, basically. I started at 23rd and I made my way all the way back down on the 1. Yep. So for those of you who go to New York, you probably recognize these numbers. Cool. So let's say that we always start at 14th. Let's say that this is actually a subway. So this is the one train going uptown. So let's say this is the one train, This is the one train going uptown. So with the one train going uptown, let's say that we always have to start at 14th because we live at 14th. And then we want to get to 79th Street. How many nodes are we going to see? Don't talk about complexity right now, but how many nodes are we going to have to cross to get to 79th Street? How many stops do we have to take? And don't count the beginning. Yeah, so we have 1, 2, 3, 4, 5, 6, 7, 8. So 14th to 79th is going to take 8 stops. Exactly. So how does New York fix this problem? Like, we don't want everyone to have to take every single stop, right? Does anybody know how the New York subway gives you an option to get places a lot faster? The skip stop train or the express train, exactly. So let's draw out the express train. So it's going to be the same exact stations, and we're actually just going to have a different line. So does anybody remember what the one train express actually does? Do you remember the stops for it? Probably not. I'll just do it. So 14th actually goes straight to 34th. 34th goes to 42nd, and then 42nd goes directly to 79th. So those are going to be the stops on the one train express. So I'm going to label that as the one train express. Okay. So now, how do we get to 72nd Street? How many stops do we take in order to get to 72nd Street? 3 stops to get to 72nd? Not 79th, 72nd. Not quite 1. So yeah, we're gonna end up taking 6 stops. So we're gonna go, so 14th to 34th to 42nd. And then we jump onto the local and we go to 50th, then to 59th, then 66th, then 72nd. So keep in mind that this is unidirectional. So in some sense, we're minimizing the total distance that we travel. That's just the way that we're going to operate with this because a skip list is a singly linked list. So we can't go to 79th and then come back. We have to go to 42nd and then go down to 72nd using the local train. So in this example, what is one way that we can come up with an algorithm on when to transfer? Any thoughts? Someone raise their hands if you have a thought on when we should transfer. If it's a doubly linked list, it would be way faster, yes, but we're not going to be talking about doubly linked lists today because a doubly linked list is just an array, so you might as well just use an array. So here we're only going to be talking about a singly linked list. We can do a peek of current.next. So let's actually, before we define an algorithm, let's say a node now has an extra thing. So nodes have a value, which is an int. We have a node pointer to next. And then we have a node pointer to express. So let me rewrite this in the right color so that you can keep track of that. So this is going to be node express. Does that make sense? So orange is all going to be the express part in this lecture, and then the white part is all going to be local. So how can we do an algorithm? How can we come up with an algorithm on when we want to transfer to the local? So in this case, we went from 14th to 42nd, and then we transferred to the local once we got to 72nd. So let's come up with an algorithm that helps us do that. Any thoughts? Y'all are still asleep? Yeah, so we're trying to come up with an algorithm. So let's say you're starting at 14th and you're trying to get to 72nd. How do we know when to transfer to the local? What does express point to? So express here is going to point from, for example, 14th to 34th. And then this is going to point from 14th to 23rd. So yeah, so if you basically start on the express, so you start on the express and say, go on express until next stop is too far. Then transfer to the local until you get to your stop. Exactly. So does this only work for ordered linked lists? Yes, this only works for a sorted linked list. And today we're going to only be talking about sorted linked lists. We're not going to be talking about unsorted linked lists. We're going to be specifically using a mechanism that will work for sorted linked lists. And we'll see why towards the back end of this lecture. So yeah, overall, and then one more thing, I'm gonna make this orange so that you can see, you can follow along with that as well. So I'm going to, give me 1 second. Ah, there we go. Okay, cool. So you start on the express and you go as far as you can until the next stop is too far. Then you transfer onto the local. So once we get to 42nd, we say the next stop is 79th. That's further than 72nd. So now we transfer onto the local and we keep going. That sounds exactly right. That's exactly what we want to be able to do in order to get to our stop with the fewest stops possible. So let's go over, give me 1 second. So this is going to be the algorithm that we basically have for 2 linked lists. So keep in mind that this is not a skip list, but this is an intermediate step that we have to take in order to define what a skip list is. So basically all we're going to end up doing is we have a head and then we have a current value. We set that equal to the head. We take the express next. So the express next is basically the next stop on the express train. If that's not equal to none and it's not equal to the goal and it's less than our current goal, then you go down the express and you keep doing that. But if it is, but if that's not the case, else if it's not equal to none, you go down to the current dot next, basically. And you keep doing that. And then it's the same thing here as what we had before. If it's equal to the goal, you return that. If it's greater than the goal, then you return none. There was no stop that we could have taken. Is all programming just variations on searching, sorting, and pathfinding? No, not at all. That's what is misleading about this class, to be totally honest with you. When you're taking your undergrad classes, it's going to feel like all programming in the world is just searching, sorting, and pathfinding, which it might be true on like some level somewhere. But when you're writing an app, an Android app, for example, you're not really thinking about how to search. You're not really thinking about what to sort. Like, you're not doing any pathfinding. You're actually just making things. So I would say all programming are basically variations on searching, sorting, pathfinding, scripting, and design patterns. And keep tuned. I don't know what the expression is. Stay tuned. There it is. Stay tuned for next week's lectures. And next week's lectures, we're actually going to be talking about design patterns and why engineering in industry is actually different than what you see in academia and what they won't teach you in academia that is going to be essential for success in industry. So a big spoiler on that, basically the topic is going to be design patterns, and we're gonna have some soft skills discussion as well. Cool, so jumping back into this, so this is how we do a two linked list search. So this isn't a doubly linked list, it's 2 singly linked lists. So this is going to be local and express. Okay. Does that make sense to everyone? Any questions so far about how we use the local and express trains to get to our destination faster? All right, I'll keep going then. So let's go into the complexity of this. So let's start over and let's say that we're defining a new train, basically. Let's say that the best train that we can, or let's say we have some base set of trains that we want to get to. So I'm going to copy and paste this original route. Dang it. Okay. So I've copied and pasted this. We don't have an express train, and the city has asked us to make a express train. Wouldn't this work on a DAG with slight modification? In some ways, yeah. So the problem with a DAG is that it's not necessarily sorted. We know that this has to work on a sorted graph, but DAGs aren't necessarily sorted, but if you have a sorted DAG or whatever, then yeah, pretty much, because a sorted DAG is more or less just a linked list anyway. Cool. So let's talk about what we do here. What is the most efficient place if we could put an express train anywhere? So we no longer have to go from 14th to 34th. We're making an express train basically. So what is the most efficient place to put our first stop? Where should we put our first stop if we can only have one stop total? The middle, yeah. Let's just put it right in the middle. So let's go from 14th to 50th. I think 50th is the middle, maybe 42nd is, doesn't really matter. But yeah, we're gonna go right to the middle. So let's say we only have one more that we're allowed to add. What's the next one that we probably wanna add? Well, before we do that, yeah, we wanna add the end, because everything should end at the end, let's say. Okay, so now we have the opportunity. The city got some extra money in some tax grants, and now we can actually add a second line. Where should the second line go? Like, where should the first stop for the second line go? Any thoughts on that? N over 4, okay. So we go from 14th to 34th. And then what about the next stop from there? 34 to 50, yeah. And then we can do 50 to 66, and then 66 to 79. Sounds good to me. And then let's say that these look like a great amount of stops. This is actually awesome overall. Let's say that we have some extra money, like the city is just rolling in dough right now. We can add one last stop wherever we want. Let's just say that we add one stop from 14th all the way to 79th. We know that 14th and 79th are both really popular, so we just add one last one that goes all the way from 14th to 79th. Cool. So now, what would we actually do in order to find any stop? So let's say we're going from 14th to 72nd. How do we go from 14th to 72nd with all of these? What's the first thing in our algorithm that we should check? Check red, okay. So check red dot next. So that's going to be 79th, but 79th is greater than 72nd. So now what do we do? Always take the biggest step if possible. Yep, great summary. So if red dot next is greater than goal, then all we do is check our green. We take our green and say check green dot next. If green dot next is greater, then we take orange. We say check orange dot next. And if that's greater, then what do? We just take the light. Exactly. So that's all. This is a skip list. It is as simple as that. All we're going to do is have multiple different variations of different routes that we can take. And then that is going to allow us to jump around a linked list much faster in a one directional sense to get to our destination in the fewest stops possible. So I'm going to rewrite this graph here, and you're going to have to bear with me for a couple minutes while I rewrite this, and we'll see what those different lines actually look like. So give me just 1 second. Sorry. Okay, so I'm going to write the actual nodes that we have here. Keep in mind that these are actually just pointers. So 14th is not going to exist multiple times, but I'm just rewriting them for the sake of example here. So let's say that we have 14th going to 34th, going to 50th, over to 66th, and to 79th. Then we have, I forgot which one's next. I think green is next. Yeah. So we say 14 goes directly to 50. And then to 79th. And then we have our red, which goes from 14th directly to 79th. Okay, cool. So the number of lines there we would probably want to be dynamic. Bingo. So this is going to be super important here. So if we only have 3 lines here and we start inserting new elements or we delete elements from our original skip list, then what's going to happen? We don't want there to always only be 3 lines, because at some point, if we have 1,000 subway stops, then 14 to 79 isn't going to be that useful anymore. So the big question here is, how do we do this in a way that allows for inserts and deletes? So we talked about why this is important from a search perspective, but how do we allow inserts and deletes? So that's the major question here. So before we answer that, let's talk about complexity. So let's talk about the complexity of search overall. So how quickly or how hard is it going to be in the worst case scenario? Let's actually not talk about the worst case scenario. Let's talk about the average case scenario. How quickly can we find the stop that we're looking for in the example that we provided? Log n, and n is the number of stops, sure. So we have omega of 1 as our best case, and we have O of log n as our average case. Yeah, so of course, n equals the number of stops. And then we say that log n is the number of log n is the average number, and the best case obviously is we're just looking for 14th and we get there right away. Sure. And then technically in this case, what is the worst case going to be? I'm not even going to write down, but let's just make sure that we know for our analysis. The worst case isn't going to be O of n still, because we can still jump. We can still take whatever routes we want and transfer wherever we want. So we can still actually do the worst case in log of n. Yeah, it's going to be the same as the average. So in some sense, this is going to be a theta of log n as the average. So that's just something to keep in mind here. This isn't necessarily going to be true for a skip list, and I'll show us why in just a second. So how do we make a data structure that supports inserts and deletes? Let's actually go over that really quickly. So let's talk about inserting into a skip list. So if we do it deterministically, does anyone raise your hand if you know what deterministic means? Nope, nobody? Okay, cool. So I'm glad I asked that question then. So deterministic means that you're always going to follow some algorithm without randomization. You're not going to follow any probabilities. You're always going to do some pattern no matter what. Now, the problem is, if we have our original graph, 14 to 79, and now we add 81, how do we know which routes to put them in? The, the answer is we don't really know, right? We don't know how to modify existing routes. We don't want to modify existing routes. We don't want to be like, oh, actually now we want to get rid of 79th on the orange and now we want to put 81 there instead. Like doing that is going to get really messy. And in the analogy of a subway, you don't really want to modify stops that other people are using. You don't want to just randomly be like, hey, we know that 66 was really important to a lot of people. Effective immediately, no one can go to 66th Street. That's not great. Happens in New York a lot, and it's not a wonderful experience when they just tell you that subway stop doesn't exist anymore. So we don't want to do that. We want to build new stops, and we want to say when we build a new stop, what other routes should they connect to? And that's what we're going to do. So inserting into a skip list is going to be actually a probabilistic thing that we end up doing. So what we're going to do is say, you always insert into the base, into the bottom level. So the bottom level is, again, the white level. So what happens here is basically going to be, we always, when we have a 62 to insert, we're always going to insert 62. So this part is deterministic. There's no probabilities attached here. We're always going to insert here because this is the subway map for every single stop on the local. We always want to insert into that one. So we're going to insert a 62 into that one. And then what we're going to do, what do you think we're going to do next? How can we do this in a non-deterministic way to make it roughly the right probabilities that everything's going to come out the right way? Any thoughts on that? A normal distribution? Let's think even easier than that. What's the way that we did probabilities and randomness in this class? For project 1, project 2, how did we just do random graphs? Yeah, and we just basically flipped a coin. So you flip a coin. If it's heads, then what we want to do is promote element, or sorry, we want to promote the level and add our node. So what this means, what promotion means, is basically we go from our bottom level, the white level, to the orange level. That's the first promotion. We're going to promote to the orange level, and we say, cool, now add it to the orange level as well. And then you keep doing this until what? So if it is to be inserted in the last place, shouldn't we at least update the red line? Not necessarily. So let's go through really quickly and then we'll go through an example. So we keep doing this until we get to tails. And one thing that I actually want to add in here is that if you need to add a new level, then you just add a new level. If new level needed, add a new level. So what this is going to look like is, let's say we're inserting 62. Now we're going to promote it. So we're going to flip a coin and say, okay, 62 is now going to be, we're going to see if we want to promote 62 to the next level as well. So we flip a coin and now it's heads. So we add it to this level now. So we add 50 going to 62, going to 66. Cool. Are we done? Do we stop? No. So we flip a coin again now. and it lands on on heads again. So now we flip a coin again and we get heads again. So now we add it to this level. So we add a 62 here. And then we're still not done. We keep flipping until we get to a tails. So we flip again and we get another heads. So let's say that we add another level here. We add another 62 here. So we get to 62nd here. And we add that. Are we done? We're on the last level. Are we done? Nope. We actually have to flip again. And now we're going to flip for the 4th time. And then we say that now we get heads again, and we end up adding it to a new skip list, or a new linked list, sorry. We promote it again. That level doesn't exist. So we add a new level with 14 going directly to 62. And then 62 doesn't connect to 79 necessarily here. 62 might just, it might just end right at 62. It might keep going, doesn't really matter. So in this case, we just know that we don't know anywhere further to go. How are we accessing the previous nodes for the other routes? We're not accessing the previous nodes at all. All we have is access to the head node. So we have 14, and that's the only one that we have access to. Because it's still a linked list, basically. What's the point of this, of doing that, of randomly promoting? That's a great question. So let's actually go through let's figure out why we're doing that, and then we'll be able to figure it out. So the bottom level, let's figure out how many nodes each level is expected to have. So expected to have, or this one is always going to have n nodes. Let's say that this always has n nodes. Okay, so what's the next level going to have? What is the expectation of first level going to have? How many nodes? Yeah, expected n over 2. And then the next level is expected to have how many? N over 4. So the second level. So what about the kth level here? How many elements are expected in the kth level? Not quite 4, not n over k either. So yes, exactly. So it's going to be n over 2 to the power k. So each level, we're dividing by 2 until we get expected n over 2 to the k. So how many levels are we going to have total? Expected number of levels. Log k, exactly. Or log n, sorry, not log k, log n. So we're going to keep going up, and we're expecting that we're going to have log n levels. And overall, we're going to have the bottom one, which is the worst case scenario. So we can always get from the start to any node, but we can use these express routes that we're building in order to get to the places as fast as we can. So now, if we do that, we're going to end up with, let's talk about the complexity of insert. So with the complexity of insert, what we're going to do is basically flip a coin over and over until we basically end up inserting in some number of levels. So let's write this down again. So flip a coin while heads, insert to next level. Okay, so what is the complexity of this going to be? What's the worst case complexity going to be? Let's start with that. Do you stop when you insert a new level? No, you don't. You stop when you hit tails. So this is a while loop that goes on heads. So you only stop when you get to tails. You may insert, 15 new levels. That is possible.
Can you say that question one more time? What's
Yeah.
the
So the question is, what is the theoretical worst case scenario that we might have? Gabe, yeah, so infinity, not realistically. So let's talk about that. Worst case scenario is this is actually O of infinity. So this could theoretically go and you could just have some coin that flips to heads over and over with a 90% chance. And unfortunately, that's just going to make, 500 million levels and your skip list is going to go to shit. That's going to suck. What are the chances of that happening? Let's talk about that real quick. So the first promotion, the chances are 1/2 if we have a fair coin. Then the second promotion is 1/2. And we keep doing that. So the kth level, what is that going to end up being? So the kth level is going to be 1/2 to the power of k, and then 1 minus that. The probability of promoting k times equals 1 minus 1/2 to the k. Exactly. So this is like almost immediately going to go to 0. So for k equals 5, we now have probability equals 31 out of 32. Okay, sorry. Probability of promoting k times is not the 1 minus. So we just have the probability at k equals 5 is 1 over 32. Oh, sorry. My computer froze. Okay, there we go. So when we have k equals 7, this is going to go to 1 over 128. Really, really quickly, we're going to see less than 1%, even to promote 7 times. So if we have k equals, 12, this is going to be in the, this is going to be roughly like 0.001%. So there's almost no chance that we're going to have more than like 12 promotions unless we have like 100,000 or 1,000,000 elements. Why not stop after inserting a new level? Because that's not necessarily the case that we want to stop at inserting a new level, because that means that new routes can only have newer elements. So we don't want to necessarily say that the newest route that's being built can only have new stations on them. We want to say we might want to future-proof these routes by potentially saying we're starting a new route and it's only going to have one station for now, because that way the probability will actually be expected the way that we want it to. One way that we do in one thing that we can do in skip lists is to prevent the worst case from being infinity. We could potentially say there is a fixed number of routes. So instead of saying that you only insert a new level, you can say terminate after inserting k level, or we already used k. Let's say you terminate after inserting alpha levels. So once you've inserted alpha levels, maybe that's 1, maybe that's 7, maybe that's 15. After you do that, you just stop and you say that's the most routes that we're going to insert with any new addition. You don't want to keep that at 1 because that's a little aggressive. Sometimes they do that in skip lists, but usually alpha is on the range of 4 to 10. And there's just some complicated math behind why. I don't know what that math is, but they've found ways to optimize that basically. Sean?
Yeah, just a quick clarification. So like with that question, why not stop after 1? Does it make sense? So like with the previous example where we had like 8 nodes and you had the red line, which was, 4 levels up or 3 levels up.
Yep.
So if you ended up like adding 1,000 more nodes, like you wouldn't have anything going from the beginning to the end. You would just have
Exactly.
one level after the 8 nodes that originally existed.
Right.
Does that make
So
sense?
I guess if you have 1,000 nodes in it, this level may not exist, and it can only have the 1,001th node in there. And all of those first 1,000 aren't going to be eligible to even be in that node, in that route, which means that you're kind of skewing the probabilities in weird ways, and you don't want to quite do that because it's just going to complicate your math a little more. Make sense?
Yep.
Cool. Awesome. So that's how we do an insert. And oh yeah, we talked about the worst case scenario. Let's talk about the average. So this is the expected average. So again, with high probability, so what that means is, i.e., as k grows sufficiently big, probability of average equals 1. So what is the average case? I'll answer questions in a second. What is the average case going to end up being for an insert? Like, what's the average time complexity going to end up being? So an insert, we already talked about how an insert is going to take O of n time in the worst case scenario, but and the average case scenario. But we have O of n as the number of elements in the linked list. And then as we promote higher, so the first one is always going to be O of n, basically. Then we're going to, oh, sorry, this is not going to be O of n. This is going to be something like O of n minus 2, n over 2, or something like that. But we can actually take a shortcut for that first insert, right? The way that we can take a shortcut, like let's say we're inserting 62 here, can't we just take a shortcut by saying jump onto the top route and search for 62 in our bottom route? So we can basically say jump onto this one and go onto the, or sorry, let's say we're inserting 71 now. So we're trying to insert a 71. So what we can do is search in the exact same way as before. We start with the top level line. We go onto this line here. We go to 62. Then we jump onto the bottom lines. We can't go from 62 to any of these. Then we go to 66. Then from 66, now we insert 66 to 71. Does that make sense? So even though we're inserting into the bottom level, we can use the top levels, the super expresses, to get to our 71 in our bottom level. Does that make sense? Raise your hand if you're confused on that. Okay, so what we're basically saying is the way that we would want to insert 71 here is we can do it the dumb way. The dumb way is to go and say, is 71 greater than 14? Yes, it is. Is it greater than 23? Is it greater than 34? We go linearly through our bottom level. But that's really dumb. It's going to take O of n time to do that. So instead of doing that, even though we want to insert at the bottom level, let's use the top levels to find the place where we insert. So we're going to start at 14. We're going to say jump directly to 62 and be like, is 62 greater than 71? No. So now we go to 62 and we go down a level and we say 62 to 79. Is 79 greater than 71? Yes, it is. So jump down a level. 79 still greater. So we say 62 to 66. Cool. 66 isn't greater. So then we go down to the bottom level. Then we say 66. And now we add the local new node. We go from 66 to 71, then the 72. So all we're doing is inserting in the bottom level, but we're using our top level linked list to find the right place to add it back into. So that being said, what is the complexity of our bottom level insert basically? Matt?
Yes, I'm sorry. Can you guys just go back to the train stations?
Yeah.
So in that case, we wouldn't insert the 71 in the orange path because 66 is smaller than 71 instead of doing the and the white path.
So that's a
we
great question. So we haven't flipped our coin yet. We don't know if we're inserting into the orange yet. So all we know is we're inserting into the light because we always insert into the light. So we don't know whether we want to insert into orange or not, but we'll get to that point in a sec. Does that make sense?
Yes, it does. Thank you.
Okay, sure. So what is the complexity going to be to do our bottom level insert, basically? Where was I? Here. So the bottom level insert, we're actually going to be able to find the place that it belongs in log n. All we're doing is searching, and then the actual insert part is really easy. All we have to do is set some pointers. So the bottom level is going to be, on average, this is going to be log n. Then every level above that is also going to be some function of like log n times some c, and then overall out here it's going to be divided by c or something like that. And one thing that we're actually going to observe is each level is going to be less work than the level above it, basically. So there's some math behind this that I'm going to gloss over, and you don't have to worry too much about this, but each level is going to be less than previous level. And the top level, or sorry, the bottom level is going to be the one that takes the most amount of work, and that's going to be log n. So our total average complexity is going to be log n plus, let's just say, plus a plus b plus c, and a is less than log n, and b is less than a, and c is less than b. So what is the total average complexity going to be? It converges to log n, exactly. So the total complexity of an insert into a skip list is going to converge to O of log n. So we can just ignore all these minor terms because A and B and C are really, really small. We don't really care about them because log n is going to be bigger than them anyway. So now we've shown that so far we see search, insert, and delete for a skip list. And so far we've seen that this is log n and this is log n for the average case scenario. And the average case scenario is 100% of cases. We've shown that with high probability, this is going to always be the case. So let's talk about the delete algorithm. So how do we delete a node from a skip list? So let's go all the way back up here. Now, how do we delete, for example, 62? Any thoughts? This isn't too much of a trick question. Yeah, so first we're gonna find it. So what we're going to do every time is find it. Matt, what's up?
So we're gonna start from the more express level, and
Yep.
we were gonna check if that node exists and within that path. If
Yep.
it does, we want to obviously delete it. But a quick question that I have, for example, in the at the last level that we have 14 to 62. In that case, are we going to delete? I don't, never mind, because 62 is there. So then we're gonna, go to the next level, delete 62, and then just point 14 all the way to 79 in that path, and do the same thing all the way to the bottom.
Right. You're super, super close. The only tweak that we want to make is, let's say that we delete this 62, the top level 62 right away. Then the next time we want to find 62 in a lower level, we're not going to be able to find it as easily, right? So what we want to do is delete from, so we want to find 62 at the bottom level, delete the bottom level, then you go up, find 62 again, delete that one, then you find 62 here and delete that one, then you find 62 here, delete that one, and then you find 62 here and delete it. So you want to delete from the bottom going up to the top so that you can keep using those express paths without destroying your efficiency. Does that make sense? So yeah, you're deleting pointers, not actual nodes, and then you only delete the node at the very end once you've deleted all of the expresses, basically. So deleting is really easy. Find node at bottom level, delete pointer. Then you go up a level and repeat. And you keep doing that until you get all the way to the top, and then you delete the node. Yep, and then deleting is the same as in a linked list. You just keep track of the previous, set the previous equal to the next, etc. So one thing to note is in the skip list that we have, each of these is actually just a linked list. So a skip list is just a list of linked lists, and it keeps track of all of these different linked lists that we have so that we can make it more optimal. So deleting, again, is just the convergence of different searches that we have. So what is the average case complexity that we have of a skip list delete? Sure, sorry about that. I can reiterate the deleting part. So what we're going to do for the delete is just start at this top level. We're going to find it the same way that we did before. We had 62 all over the place here. So what we're going to do is just take 62 and find it in the bottommost level. So we're going to find it the same way as before. We jump from 14 all the way to 62. Then we go down, oops, sorry. Then we go down here and we'd be like, aha, we've already found the 62. Now we delete the 62 in the bottommost level. So we delete this at the bottommost level. Then we walk up the skip list and say, let's delete it from the next level. We delete 62 here. Then you walk it up one more and you delete this 62. Then you delete this 62, and then you delete the final 62 at the end. So you're deleting the pointers as you're walking up the skip list. And then once you've deleted the pointers all the way at the top, once you get to the top, you just delete the actual node itself so that you free up that space. So with the complexity of delete, let's think about deleting as the opposite of inserts. In inserts, we insert at the top, or we insert at the bottom and then work our way up. With delete, we delete at the bottom and then work our way up. So if you don't find it in one of the levels, then you have to move on to the next level up. Yeah, basically you just have to keep moving on all the way up the levels. So deleting is actually also going to be a log n operation, because it's the exact inverse of insert, basically. You're going to search for the node, then you're going to insert it, or you're going to search for the node and you're going to delete it. So all three of these operations are log n time. Can we demonstrate an insert to the leftmost position? Sure. I'm not sure what the confusion there is, but let's do that. So if we have a leftmost, so if we have a 7, if we have a 7th avenue, then all we're going to do is say, we always insert here. So 7th is going to be our new head, and it points to 14th as our next. We flip a coin and say, is 7 going to be, do we want to promote 7? And let's say we do want to promote 7. Then we end up saying 7 goes up here, and we add a 14 here. And then we go to 34th. So we just keep doing that recursive, or we keep doing that iteratively and go up the chain and say 7 is our new head for all of those chains. Does that make sense? Cool. So let's go back to our skip list lecture. So I've left some pseudocode for insert, and we talked about the complexity. We went through to delete as well. Basically, all we're going to do is search and delete for the value. And then this is also going to be roughly log n, but there's going to be some additional complexity that we talked about, but we don't have to worry about those because those are trailing terms. Log n is the overpowering term overall. And I said we're not going to prove this, but we pretty much proved why this is going to be almost 0 at high values of n. So again, this is 1 over 2 to the power of n is the probability of not ending. And that's going to be roughly 0 for n greater than like 7 or something like that. So let's talk about why this is important. So here's a chart that demonstrates all of these different values of unsorted arrays, linked lists, sorted arrays, sorted linked lists, and skip lists. So some of these have better performance. For example, like an unsorted array insert and a linked list insert are both constant time. However, none of them have log n performance across the board. Everything in the skip list is actually log n. And as you saw, it's actually super easy for us to actually implement it. It's incredibly easy. All you have to do is have a list of linked lists. And then that list of linked lists is going to be your skip list. So your average case complexity is actually going to be log n for all 3 operations. And no other data structure that we've seen in class even sort of comes close to doing that. The only other one that comes close to doing that is a binary tree. But with a binary tree, you have to keep it balanced to get log n for all of these. And you saw yourself in project 1 how hard it is to actually implement an AVL tree. So a skip list could have saved you a lot of work if we had just done a skip list instead of an AVL tree for project 1. So that's the beauty of a skip list. However, the biggest difference is basically that there is additional space complexity because we have to hold a list of linked lists instead. Sean?
Just to double check the space complexity, because you're not duplicating anything, right? You're just holding extra pointers. So it's just the pointers that are the extra space.
Yeah, but the pointers still have to have some space associated with them because you have to know how many references you want to hold. So
Right,
that
okay.
is still additional space complexity. Yep. And don't forget that a linked list node is pretty much a pointer anyway. It just has an integer that it holds, so it doesn't.
That's
really.
right. Yeah.
Does better time complexity trump any extra space complexity for algorithms? Not just this. It depends. If you have an algorithm that's like v factorial space and it can get you from O of v to O of log v time, not great. But for the most part, it's usually true, but not for something that is like an incredibly huge amount of space for not that much added time benefit. Make sense? Cool. Today's daily quiz is going to be to, in your own terms, in your own words, compare skip list to a hash map, or sorry, a hash set and a balanced binary search tree. So I want you can use complexity to do that. You can use anything you want to describe the advantages and disadvantages. So the advantages and disadvantages of a skip list versus a hash set and a balanced binary search tree. What are different things that might be allowed in a skip list versus a hash set versus a balanced binary search tree? So that's going to be your daily quiz. All right, and don't think I forgot. I'm never going to forget this slide. Why do we care? Why is this an important data structure? So there are a lot of reasons I have for this one. You probably won't get all of them, but let's get started with some of the reasons why skip lists are pretty cool. Sean?
Well, basically, if memory is not a big issue, anytime you're using a linked list, you just switch it over to a skip list, and you'll get better performance all around.
Yeah, so you can almost always use a skip list versus a linked list. Sure. And Matt, did you have a thought?
No, it was pretty much the same though. So
Okay, cool. Yeah, so David actually mentioned a good point, which is at the database or compiler level, you probably don't want to use a skip list unless you have to. But overall, you probably can just use a skip list. That's a great question. I don't know if skip lists exist in any standard libraries. Obviously, they exist in some libraries, but like I don't know if they're in the standard library. This is a pretty advanced data structure, and most standard libraries don't support randomized data structures. Most standard libraries only support data structures that guarantee some worst case performance or something. So that's why people tend to shy away from using skip lists, because theoretically this could result in really, really bad runtimes. And you don't want that in a standard library, because that could like crash computers if you introduce a bug, or if randomness has a problem or something like that. Cool. So there are a lot of different answers that I had. So firstly, they are super easy to implement, and they have awesome average complexity for every operation that you have. This is super cool because it will take you like an hour to implement a skip list maximum, and then you can have average complexity for each operation. Skip lists are an introduction to a very, very cool part of algorithms and data structures that we haven't covered in this class. It's the first non-deterministic data structure. It's a randomized data structure that uses probabilities all over the place, and it's actually used way more often. This is way more often the case that we do algorithms and data structures like this that optimize for the average case. We say average case is true 100% of the time. Don't worry about the worst case. Like there's such a small probability that it's going to happen that we don't care about it. So this is going to be very reflective of what industry level algorithms and data structures look like more often than not. And then skip lists, one thing that I really like about skip lists is they're relatively new. Skip lists are only 4 years older than me. They were founded in 1989, which shows that the field of data structures is constantly evolving. In my last lecture, someone asked, what does it mean to create a new data structure or algorithm? You can see that skip lists is a created algorithm. And in a lot of ways, honestly, it's very intuitive. We basically found it, we basically invented skip lists after looking at the New York subway stations, and we were like, hey, we can just replicate this and then make an algorithm based on that. So this was actually founded by I believe a TA or a PhD student, and they ended up finding this sweet new algorithm that has remarkable performance implications on linked lists. And then lastly, they are one of my favorite data structures. I really like them. They're just a very, very cool phenomenon that takes advantage of a lot of basic concepts to do like these average computations that are very, very cool and reduce everything to log n, which is an excellent time complexity. That is why we care. And here are my references. So MIT's lecture on skip list. So funnily enough, I think I may have been sitting in that lecture hall during that lecture. They were definitely recording, and that was my professor for that class. So I might actually literally be in that video, which is pretty funny. And there's an article describing the trade-offs of a skip list. And then here's another article that goes into the advantages of a skip list as well. Any questions on skip lists, or any open-ended questions right now? No? Good to go? Sweet. Enjoy your week and weekend. I will see you for the final 2 lectures next week. They're going to be fun. Well, one of them is going to be fun. One of them is going to be important. But yeah, I would encourage you to come to those. Again, all of these exams are still covered on the all of these lectures are still covered on the final. So please make sure you're paying attention. Because there's going to be at least one question that covers these topics. So including the next 2, yes. So all of these lectures will be covered on the final. Yep. It's not going to be a major part of the final, but it is going to be on the final. So make sure you're paying attention. And that's it. See you next weekend. Bye. Or sorry, see you next week, I mean.